Okay, so further to discussion on shadowing. So we'll proceed on Linux Mint. Okay, so we'll cover the topics. Okay, so we'll cover shadowing in OpenGL and camera and the light model and frame buffer architecture, depth buffer, texture map, shadow acne, and how shadow acne is kind of that we can remove, and adding bias. So this is one of the solution for the shadow acne. So that we'll see. Okay, so this is camera that is placed at origin, and this is light source. It is placed at some hypothetical point XYZ. So if light falls on a surface, then on the another surface it makes a shadow. So this surface has a color yellowish, and then there is a shadow. Shadow is because of this spherical surface, and it is because there is a light source here. Okay, so there is a camera that is placed at the origin. So in OpenGL analogy, we can kind of think light as a camera only. So from camera, photograph is being taken, and this portion cannot come on any another surface. If this portion cannot come, then this is a shadow. Okay, and so this is kind of a light analogy, and a fixed camera that is placed at the origin, and if this surface, another surface is getting obscured by this surface, then this surface cannot be drawn, that portion cannot be drawn. So that is the difference between camera and light. So both are kind of, they look into the scene. When camera look into the scene from the origin, then the surfaces that is obscured, they do not pass the depth test and they do not come. Whereas when it is light, then when we draw the surfaces, and if any region is getting obscured, that is drawn as shadow. Okay, so how kind of we can achieve this effect? Like how we can achieve the effect of shadow? So that we'll see. Okay, so if this is camera and this is light, if I see from the light perspective, then it would look like this. Okay, so if I see from the light perspective, from the light source, it should look like this. And where the actual thing is, that is the sphere where the light is falling. So underneath there is shadow. So we are talking about how light sees. If camera is placed at the light location and then it look in this direction, then it sees a sphere, and then it is followed by a kind of another surface that is a plane. So if camera is placed as the light source, then it would see exactly like this. Okay, and where this shadow portion is obscured by this sphere. Okay, so we'll proceed. Okay, so OpenGL is nothing but it's a kind of mathematics. There is nothing light and a ray of light, and there is no physics here. Okay, so OpenGL, there is no physics, there is no chemistry, there is no biology. So it's a pure mathematics. So I'm in kind of set of vertices and matrices, and then matrix addition, multiplication. Okay, now can we think light? So light is here. Can I place light here? Light is at x, y, z, and how I look from the light perspective. If I look from the light perspective, it would see like this. But this is not a sentiments, right? Means it's a pure mathematics. So how we can kind of solve this? How a light, if camera is placed here, and when it sees the sphere and when it sees the surface, then it would see like this. How it would happen? So we can think like the light source is placed at the camera location. If light source is placed at camera location, so this is camera, then white is light source, then it would see exactly like this. So light source, okay, now we can think like light source from here, it got rotated, transformed, and it came here. Or from here, we do some rotation transformation and we bring the light here. Okay, what I'm trying to say is how I can think that from light it would see like this. So one solution is I have to bring light at the origin. If I bring the light at origin, then it would, if you see in z direction, then it would see like this. How I can bring light from x, y, z, that is the hypothetical distance, to the origin? If that is the idea, then we have to push some rotation and translation into the model view matrix, and light would come here. If light comes here, then it would see the image like this. Okay, so now we talked about a series of rotation and translation that need to be done on the light source, so that light source come at the origin. Okay, so if this is true, okay, so further we'll take it. Now if light source is here and it can see the two surfaces like this, and if I rotate the light source along the y direction, then this surface would become like this. Okay, so the surface would become like this. So if light source is consistent here and I rotate the axis y along the y axis, then these two surfaces would become like this. Okay, now So that I can say kind of a GL rotate. So GL rotate along y-axis when the light source is placed at the camera. Then whatever we are seeing, the two surfaces, so two surfaces would turn like this. Okay. So means this is how it changes. So rather than, means I gave one example like how rotation and translation happen. So a simple case is if I rotate along y-axis, then this diagram would become like this. Okay. Now rather than I do rotation and translation series of, so that this light source would finally come here, the light source from the origin, it would come here and it would start looking like this. We can use a ready-made kind of utility from the GLU, that is GLU look at. If I use this, then GLU look at takes care of transforming the light source from origin to this position. Okay. And then when it comes to from origin at this position, certainly it does changes in the model view matrix, and then it can look like this. It will give kind of a similar impression where the light source is placed at the origin and looking in the negative z direction. So we'll use GLU look at. So GLU look at, if you see the grammar, then GLU look at first talks about kind of where the light is placed, in what direction it is viewing, and then what is its kind of up direction. Okay, so this light source, it can be up in the y direction, it can be up in the x direction or in z direction. It can be placed at x, y, z, and where it is looking at. So I can say that it is not looking at the sphere, it is looking at the origin. Okay, so this light source is looking at the origin and light source is placed at x, y, z. So it's a kind of a camera analogy and it's up vector. So that is in y direction. So if I do that way, then now it is responsibility of GLU look at to do these rotation and translation, rather than we do the rotation and translation in the light source. Okay, so we can also do rotation and translation of the light source, so that light source would appear here, and then how it would see the surfaces, then it would see the surfaces like this. Okay, so rather than we doing the rotation and translation, GLU look at does the rotation and translation. We have to provide some input and then we get series of rotation and translation. Okay, the final aim is that we have to look from the origin perspective. Why we cannot look from this perspective? That is the question. So why I cannot look from here? Why I have to come and look from the origin? Okay, so that I can view the two surfaces like this. Why I can't see the two surfaces from here only, from the x, y, z? Why I can't do these two surfaces like this? Okay, why I need to do kind of so many transformation and bring the light source at the origin? Okay, so we'll understand little more now. So in OpenGL, everything is placed at the center. Okay, so OpenGL starts with a concept where everything is placed at the origin. Model and camera. Camera means view. So camera and the model both are placed at the origin, at the beginning. Now these models or surfaces, one surface, another surface. Now they got transformed and rotation and they are into the scene now. Mr. Camera is also got translated and rotation, and it came here. Okay, I think we can see kind of in little minute way. So camera, so this is violet color, this is the camera, and this I believe yellowish color. So this is model. So camera from the origin, it came here. This is what we are doing. Means the light source from the origin, light source was kept at the origin at the beginning, and light source came here. Same way, models, they also, so there was rotation and translation in the camera or light source, it came here, and model also, it passed through rotation and translation, and it came here. Now, if I manage this camera through one matrix, and if I manage this model through another matrix, then there are two matrices. One is called view matrix, one is called model matrix. Okay, I think it's a good idea to see our tutorial, video tutorial on kind of these transformations and model view matrices. Okay, so now we have to maintain camera matrix, that is the view matrix, and this surfaces matrix, that is model matrix. Should we do this? That is a big question. I mean, if we see the actual mathematics, if we go for one more variable, complexity means I have one variable, A equal to 10 and A equal to this, A equal to that. If I introduce one more variable, B, okay, then complexity grows in GP, geometrical progression, not in AP. Okay, I think it's AP. And it grows in GP. So it's not a kind of fashion to introduce variables. If we introduce variable, then very quickly it will go out of human brain. Okay, and at the end, program never executes on computer. Okay, so this is a false belief that at the end computer has to execute the program. We can introduce variable as many as we want because it makes our life easy, and let the computer do its work. So I think it's a worthless statement. So everything gets executed in the programmer's mind only. So if programmer cannot execute the stuff in his own mind, okay, then computer cannot also execute. So computer is less powerful than human. I mean, this is how programmer should think. So if it is going out of the kind of control of a programmer, if I keep on introducing variables, then tomorrow if computer runs very nice, then output is coming very nice, then there is no problem. But if output is not very nice, then programmer won't be able to debug it. He cannot modify it because anyway it is out of his mind. Okay, so it's not a fashion that we introduce matrix and matrix. So can we club camera or view and model in one matrix? Okay, so now the idea is that can we keep the camera static at the origin? Camera is static at the origin. Camera cannot move. Whatever we want, we have to achieve everything through the transformation in the model only. So what we are seeing here, when camera is viewing from here, at the end, this whatever we are seeing, this is the Z direction of the camera. If this is the Z direction of the camera and camera is viewing like this, then why not we place the camera at the origin only and let model move like this? Now can we change the model matrix and view matrix to one matrix called model view matrix? In model view matrix architecture, view cannot change. View means camera. Camera always static at the origin only. Whatever you want to achieve, you have to do the transformation only in the model. Okay, so model can do any kind of acrobatic action in front of the camera. Camera cannot move. So we'll stick to that solution. Camera cannot move. So if I consider light at the beginning only, if I consider light as camera, then we are moving the camera. That is not the idea. Okay, there are two camera now. One camera through which we are actually seeing the picture, and light is also behaving like a camera. If light is behaving like a camera, camera cannot move. Okay, if light is here, then light is anyway, it is seeing the model like this. If it is seeing the model like this, then we'll place the light also at the origin. If I place the light also at the origin, okay, then to get that similar effect, we have to do some rotation and translation into the model so that it would appear like this. For time being, from the light, if I consider camera is here, then for the time being, we have to do translation and rotation in the model itself. That is this translation and rotation. That is GLU lookat. So GLU lookat make us believe that light is placed at the origin. If light is placed at the origin, then what translation and rotation we have to do in the model so that it should look the same way as, okay, so if light is here and whatever light is seeing the model, if light is placed at the origin as a fixed and whatever it is seeing, if that I have to kind of emulate, simulate, then what is the rotation and translation I have to do in the model? That will achieve through GLU lookat. It's a ready-made kind of API, and it is not part of OpenGL. It is part of OpenGL, I think, utility. It's not GLUT. It's not OpenGL utility toolkit, but it is OpenGL utility. So that we will use so that we can happily place the light here, transform, then rotate the light here so that I can see everything in the -z direction. Okay, so that is the concept. Now it is kind of we have the kind of the control in our hand now, because we are born and brought up in a way that camera cannot move. If camera cannot move, then everything has to be moved in the model only. If that is the concept, we maintain only one model geometry. If that is the concept, and if I consider light as a camera, then light I have to bring at the origin. If I have to bring the light at the origin, then how much transformation I have to do in the model so that model should look like this, the way it should have been looked from the light source. So that we will achieve through GLU lookat. Okay, so fine, so good. So as at the beginning I kind of discussed that shadowing is not a difficult task. Shadowing is a matter of research, and it's a matter of research because it's very intricate. If we miss a single point in shadowing, then we would pray that there should not be any shadowing. Okay, it's very intricate. Someone has to understand full concept of matrices, transformation, then texture, then texturing, then depth, then various testing, and then camera analogy, then pixel densities, then resolution of your screen, then viewport, then projection matrix, then model view, every minute detail, all the matrices, model matrix, view matrix, projection matrix, how matrices they change when we go for translation and rotation, what GLU lookat, how it modifies the matrix, everything. If you miss one point, then shadowing is out of your control. Okay, so in kind of general convention, people call it's a matter of research. Okay, so that is how it is matter of research. Okay, now how we can, so now we understood that why we use GLU lookat and why we want to place light at the center, because this is how we are brought up in OpenGL, that view must be at the center. There should not be two matrices, there should be only one matrix, that is the model matrix, and we call it model view matrix. Okay, now, so if light is placed at the center, origin, then it sees the model like this. Can we think whatever the light is seeing as a raster value? Okay, so this is a raster value which is filled with 1, and whatever object it is seeing, the distance from in the z direction. Okay, so this model is placed in the z direction. This is x direction. This is y direction. And depth wise, this is z direction. So in z direction, if I look from the camera light, then everything is filled with a value called 1. That is the white that I am showing. Okay. Now when it sees the plane, that is yellowish plane, that is at distance of 0.7. Okay. So this will be decided by projection matrix. So when projection matrix we specify like GL ortho or GLU perspective, I think better we talk about GL ortho, then we give the near and far plane. So if I see the near and far plane, the far plane is 1. If far plane is 1, then what is the ratio from the near and far? So if I give near and far 1 and 100, and this guy is placed at 70, then this is the candidate of 0.7. And this blue sphere, it is placed at 40, then this is the candidate of 0.4. This is how it would it will create a kind of raster data structure. Can we think like this? So from the light source that is placed at the origin, looking at the minus z direction, then everything what comes into is seen, that is white, means that is 1. And then wherever the model is placed, that value will place in the respect to the 1. So if I say that okay, thank you. Okay, so if we talk about a projection matrix, then projection matrix is nothing but from one point. So from one point a person is seeing in minus z direction. Okay, so if he is seeing in minus z direction, so there is a near plane and there is a far plane. Okay, so it make a cube. I don't think I should be able to draw it. I hope so. There will be a cuboid. Okay, I think that's enough. So there is a cuboid, and inside the cuboid models are placed. So this is near and this is far. Okay, if far is 100, okay, and I want to fill this raster data, then this yellowish color is at 70 and Mr. Sphere is at 40. Okay, this is what I want to say. Now, if that is the case, then our kind of raster data can be filled like this. So 0.4, 0.4. So sphere is at the center. If I have like this, okay, so what we are trying to say, if this light source is there, I bring it to the origin, and then whatever we are seeing, it becomes like this. Then we fill a raster data, and depending upon the distance from the camera, so 1 is maximum distance where there is no object, and then 0.7 and 0.4, it would feel like this. Okay, we'll proceed. Now there is an arbitrary red point. Can we see the red spot? So there is an arbitrary red spot. Now this red spot is seen from the camera, and red spot is seen from the light. From the light, okay, now red spot is a candidate for shadow. Can we see? Actually, red spot cannot be drawn. Red spot can be seen from the camera, but red spot cannot seen from the other camera, that is the light source. So if it is seen from the camera, then it should be shown. But if it cannot be seen from the light, then it should be shadow. If it cannot be seen from the camera, then it should not be shown at all. But it can be seen from the camera, it cannot be seen from the light source. It should be shadow. How we calculate the shadow? Now, for any vertex, from any vertex that can be seen from the camera, it's fine. Means it's a candidate to be shown. Now, we will do the translation of the light source and rotation, and we bring the light source here. And then light source sees like this. If it sees like this, then it cannot draw it. If it cannot draw it, but drawing happens not from the light's perspective, drawing is happening from this camera perspective. There are two cameras. Then it should come as shadow. Okay. So I am going to compare from here. So red spot, okay, so red spot distance, if I see the red spot distance from the light source, if this is 0.4, then this is 0.7. Now, okay, can I talk more now? So if this is the camera and I am talking about this pixel should be drawn or not? It should be drawn because it is in front of the camera. What should be the value of the pixel? Now camera raised its hand. Camera just can say that I can view it. But I don't know. Means it looks red, but I don't know what color it should receive. Now this went to responsibility of the another camera. That is the light. Now light is transformed, rotated, and it came here. And then he is seeing like this. Now where the red spot is, okay, where the red spot is, red spot is somewhere here, that is obscured by this sphere. So red spot cannot be shown. So camera number 2, that is the light. Camera number 1, that is the primary camera. I can say my eye, the eye of the viewer. He is saying, I can see this red spot. I want to see this. I want to draw this pixel. Now, light source is it is referred. And light source is saying, light source is transformed to the camera for some time. I mean, temporarily. And then it is looking at its raster data. And then it is finding the red spot somewhere here. And red spot distance is 0.7, where 0.4 is already filled. So camera can say that your red spot, what you are showing me, I mean the light which is placed at the origin now, it would say the red spot that what you are showing to me, I cannot see. So two cameras. Camera 1 is trying to draw the pixel, and then camera 2, that is the light that we brought temporarily to the origin, and then we saw in the Z direction, and then it is saying I cannot see. If it cannot see, then those regions, we collect those pixels which light source cannot see, those should be drawn as shadow. So two camera. One camera is saying, like I think we saw in one diagram, where there is a surface which light can see. There is a surface which light can see, but this surface cannot be seen by camera. So this camera is the boss. This camera is secondary. Light camera is secondary. This boss is saying that I cannot see this model. If it cannot see this model, then it is gone. There is no question of shadow or light. Okay? But if a pixel is in front of the primary camera, then it will say that it's a candidate for me. I am going to draw it. Then it refers the another camera, that is the light source. Temporarily we bring the camera at the origin. Through GL you look at, and then we say, sorry sir, I cannot see. So in that case, we come to a conclusion that pixel color would be shadow color. I mean, I can select the shadow color. This is shadowing in OpenGL. Okay. So what we see from the primary camera, so that should be visible, and then we go for the light camera. Through GL you look at, through series of rotation and transformation, we bring at the origin, and then we refer, since we have created a hypothetical raster and we filled it with the data, so then that red spot we refer and we say that, sorry, it's not visible, and then it becomes a candidate for the shadow. Okay, so what a camera, so we can do kind of a transformation of this raster into actual image. So white color is 1, then 0.7 is little shadow, little dark, and 0.4 is dark. Okay, so we are done. Means this is shadowing concept. So whatever we are talking about, this hypothetical raster data, hypothetical two-dimensional array, who is going to maintain this? Who is going to kind of draw it? Okay, so we'll come to kind of frame buffer concept. So frame buffer concept is happening behind the scene that we don't see. So when we bring OpenGL stuff, then frame buffer concept happens that we don't see. So by default, we get a frame buffer. What is a frame buffer? Frame buffer is a data structure. Frame buffer is not a buffer at all. Okay. So frame buffer is a data structure. And this data structure has actual buffers. A buffers means a kind of multi-dimensional array, single dimensional array, where the kind of memory lies. So depth buffer, color buffer, stencil buffer, accumulation buffer. So we consider frame buffer as a structure, C structure, and it has fields: depth buffer, color buffer, stencil buffer, accumulation buffer. Depth buffer is not a buffer at all. So it's a kind of just a container of buffers. So depth buffer, color buffer, stencil buffer, accumulation buffer. Whatever we are trying to do is a candidate of depth buffer. Okay, because we are seeing in the Z direction, we are trying to draw the depth. So it's a candidate of depth buffer. Now, so by default we get one frame buffer. In that frame buffer we have depth buffer, color. Whatever we are seeing on the screen, that is the color buffer. Okay, what we don't see on the screen, that is depth buffer, stencil buffer. So these are kind of intermediate buffers, and they are referred so that a final pixel will go in the color buffer or not. Okay, what is final pixel? What is the initial pixel? What is primary pixel? So that we will see. So our monitor is connected to the color buffer. Okay, behind the scene these buffers are there. So mathematics will happen on these buffer, and if it passes through, then it will be copied to the color buffer. Now we are not interested in color buffer, stencil or accumulation buffer. We are interested in depth buffer because we want this raster data. That is possible only through depth buffer. Okay. Now we'll talk about more grammar. So I have a kind of a surface. So this is a surface. Surface goes through some kind of transformation. So there are 3 vertices. Vertex, one vertex, another vertex, and there is a third vertex. There are 3 vertices. If there are 3 vertices and it's kind of a primitive with GL triangles, then it is a triangle. If it is a triangle, okay, now we can do transformation on the vertices. OpenGL is a game of vertices. OpenGL is not a game of edges and surfaces and this and that. Okay, OpenGL is a game of vertices. Like electronics is a game of resistance. So OpenGL is a game of vertices. So we can do transformation on the vertices. One transformation is done, then we can draw the triangle again. Triangle is not getting transformed. Vertices are getting transformed. So after doing the transformation, okay, now we receive a new set of vertices. Now we can estimate the surface. So this is kind of, we can say that this is transformation. Okay, so transformation happens generally in the vertex shader. Now we are ready with the final transformation. Then it comes what would be the pixel inside it. So it depends upon what is the pixel density of our screen. So those many pixels will be contained inside the surface. If there are pixels, then there will be color. This is fragmentation. Okay, fragmentation is when there are 2 shaders. One is geometry shader. How vertices are transformed to resultant vertex. Now once vertex is ready, once surface is ready, then how all the pixels inside the surfaces will be colored. So that is fragment shader. It is not pixel shader. It is fragment shader. For each pixel we have colors: red, yellow, blue, green, and so and so. Okay, so our geometry shader, our vertex shader or vertex shader does geometry, bring the new geometry. Okay, then fragment shader, whatever the pixel, that is rasterization it is called, whatever the pixel estimates are inside this, those are getting colored. Once they are colored, now they should be shown on the screen, but they cannot be shown on the screen because like this is one surface that is triangular. Like this there are many surfaces. One surface is above another surface. Then that surface is above another surface. Like this so nice triangle is, but it is behind one rectangle. If that is the case, few pixels cannot be shown. So on the color buffer, we cannot copy it as it is. Because if I copy it as it is in the color buffer, then triangle has to be shown, but it cannot be shown. So now we will talk about the Z value, the depth value of each pixel, and it will go in the depth buffer. So from the fragmentation is nothing but each pixel color. Each pixel color has a depth value and it will go in the depth buffer if we have enabled the depth buffer. Followed by stencil buffer, accumulation buffer. Okay, a stencil buffer is a kind of one stencil we place and we see if it passes the stencil. Like that accumulation buffer, we have series of images. Okay, whatsoever. So we are talking about depth buffer. So if it passes the depth buffer, then only it is not passing the depth buffer. Okay, some reason is getting obscured in the depth buffer. Okay, like this is the beginning what we saw. Okay, so this is a yellow surface. It is a yellow sphere, but it is not passing the depth test at all. So it cannot be drawn. Even though fragmentation is happening and there is a yellow color. Okay, if that is the case, then depth buffer would not pass certain part of the fragmentation pixel and it will be obscured because this rectangle has less Z value. this is kind of analogy of frame buffer. Then it comes to color buffer. Frame buffer dot color buffer. I am saying frame buffer dot depth buffer, stencil buffer, accumulation. So whatever is the resultant of the fragmentation, so I think I can name it. Okay, so thank you. So this is the, so I can write here. Okay, so this stage we achieve. So this stage is transformation. And this is achieved in vertex shader. Whereas this stage is called rasterization. Once transformation is finalized, then this process is rasterization that happens. Okay, it doesn't happen in any kind of shader. So this is rasterization. Once rasterization is done, then each pixel should receive a color. So rather than we saying a pixel receiving a color, we say that each pixel is receiving a fragment. So now pixel is termed as fragment. We don't call it pixel because it is not going to the color buffer. If it goes to the color buffer, we name it a pixel. So this is fragment shader. Okay, where each pixel after rasterization it is receiving the color, but it will not go to the depth color buffer if it is not passing the depth buffer. Okay, so like we saw. Okay, so I can save it. Like we saw, fragmentation happened for this surface and yellow color was assigned, pixel value, everything was done, but it didn't come to color buffer because it was kind of rejected by the depth buffer. Okay, now we are ready. So can we maintain? The idea is how we can maintain this raster data. We can maintain this raster data in an image. So we can have a kind of a separate frame buffer data structure. Anyway, we have frame buffer data structure in OpenGL. We can instantiate it. And after doing the instantiation, we have depth buffer, color buffer, stencil buffer, accumulation buffer. Okay. So we will just keep the depth buffer and we will mute the color buffer. We don't want color buffer because we are interested only in the depth. Okay, because we want this raster data. This raster data, either we do all the mathematics or we find some kind of feasibility that is already available. So if I have a camera that is, light camera that is placed at the origin, okay, then I have a projection matrix, I have a model view matrix, then I can draw it. If I can draw it, then I can draw it on an image. An image, all the texture of the image would contain this value. So far are 1 and then all the depth will have this value. It's possible that will show. So if I disable color buffering, enable only depth buffering, and then I try to draw this diagram showing some projection and model view matrix and map this to a texture will have this value. Because this is what we are drawing. And this value we need it. Okay, once I receive this, then this calculation is possible, what we showed. So we are using ready-made fundamental of frame buffer concept. So we will, anyway, we have one frame buffer that we are seeing. We will instantiate depth frame buffer. We will mute color buffer. We will let depth buffer move ahead. And then we will place our light as a camera at the origin and will take the picture in the frame buffer. And that picture will save in a texture where each texture will have this float value. Then we get the raster data. Okay. We'll draw the raster data, what we receive in the texture. And it should be like this. Okay, one raster data is okay. So one raster data is ready, which is the texture. Then we are ready. So once light is here, then it would see blue color sphere, yellow color kind of plane, but there is another sphere that is red color that is behind the scene. So that would not appear as a depth test, since it is not appearing as a depth test inside the new frame buffer. So one frame buffer, so there are two frame buffers. Okay, one frame buffer is maintained by this camera, that anyway we have one frame buffer we will instantiate, and that is solely for new camera, that is the light camera. So in light camera frame buffer, we are seeing the projection matrix, model view matrix, we are seeing the image like this, we are placing the image in a texture and we'll use its texel as distances, and then we will use as a reference when we draw the final. So when we draw the final from the camera, that is called final pass. Two passes. One pass will generate the depth, and final pass, that is from the camera, actual camera, when we draw any pixel. So from the actual camera, this is the final pass. One pass is light is placed at the origin and we take a picture, and this picture is a frame buffer, new frame buffer, we save in a texture and we have texture data. And in the second pass, that is the camera, the actual camera. Now for any pixel what we are seeing, this pixel we will refer in the texture map that is taken from the light perspective, and we will see this pixel's depth value. Okay, so let's consider this as initial phase. So in first phase, we'll bring this light at the origin. So in the first phase, we'll bring the light at the origin and we take the photograph, and this photograph will have all the model's depth in a data in a buffer. So buffer will save, buffer is saved. Now in next pass, now camera is actually it is drawing the scene, and now pixel by pixel it is drawing. So for this surface there is a red pixel. Okay, when there is a red pixel, it is saying I am okay. When it is okay, then it is going to light. Now we'll rotate the light again. We'll rotate the light again. First pass is over. We'll rotate the light again and we'll estimate the depth of the pixel, that is the red pixel what we are seeing. So in the final pass, first camera says okay, I am okay with the red pixel. Then light is transformed, rotated, and light is brought at the center, and then red pixel that is behind the scene, it is kind of coming in question again, and its depth value is calculated. Now depth value is referred in the texture. So depth value of the red pixel is 0.7. So 0.7 is here. It cannot be drawn. If it cannot be drawn, so there are three things. One thing is from camera, what is the idea about the pixel? If it can be drawn, it cannot be drawn. Next idea is light is coming at the camera, and then it is seeing the red spot like this, and then its distance is measured. Third thing is that distance and again the placement in the raster where it is. So if it at the center, then it is already occupied as 0.4, but its distance is 0.7 because red color lies in the behind surface. If that is the scenario, then it cannot be drawn. If it cannot be drawn, then what can be done? I would say please draw it as black. I would say please draw it as green. I would say draw it as blue. My shadow is blue. I am a new inventor, and whenever sun falls on me, my shadow becomes blue. My shadow becomes green. It is up to me. Okay. So three things. One thing is first we generate this raster data, and then Next time when we see any pixel that passes through the camera, primary camera, then we bring back the light again. So light is coming here 2 times. Okay, first time light camera is coming at the origin to draw the texture. Second time it is coming here to see the depth of the pixel from its own eye, and that depth and its location is compared in the texture what we have got. And then if it passes through, then it says the camera, then okay, it passes through, you can draw. If it doesn't passes through, then you can draw as a black, and then it becomes a shadow. Okay, so it will be followed by now real programming that we'll see. So we have covered shadowing in OpenGL, camera and light source model, frame buffer architecture, depth buffer, texture map. Okay, so post we'll see shadow acne, means shadow may not be pleasant what we want and what we can do.